to start so people know that. Hello, everybody. Okay, so if everybody would please have a seat, we're going to start the session. Okay, let's just give one more minute. All right, so this is the applications and IoT session. We have 4 very interesting talks. First speaker is going to be Radhika Mittal. Radhika is actually substituting in for the authors who unfortunately were not able to make it because of immigration problems. So I want to thank you for accepting to give the talk. And she's going to be telling us about AWStream adaptive wide area streaming analytics.
Thank you for the introduction, Mohammad. So hi everyone, I've been given this opportunity to present this really cool work on adaptive WAN streaming. This work was done by Ben Zhang, Junchen, Sylvia, Ratnasamy, and Wawrzynek and Edward Lee at UC Berkeley. Unfortunately, none of them could make it to SIGCOMM this year, so I'm presenting on their behalf. Now, before I start, I just want to say that all of these slides have been completely made by Ben Zhang, except for this one. And he also gave me a very detailed script on what I'm supposed to say on each slide. So please sort of think of Ben when you listen to me say his words. And we'll start. Okay. So wide area streaming analytics refers to applications in which data is generated on end devices and transported across the wide area network for processing. Examples include machine logs processing, mobile applications, IoT applications that use the cloud. Now, these applications generate a large amount of data that challenge the underlying resources, which is basically the scarce and varying WAN bandwidth. So on the demand side, in early 2009, Facebook reported that more than 25 terabytes of machine logs are generated every day that needs to be processed across the WAN. A recent work focusing on electric grid monitoring reported 1.4 million data points per second. For video surveillance, each camera requires roughly 3 Mbps bandwidth. And quoting a recent study, measurement study from Meraki that was published in SIGCOMM 2015, Dropcam has the fewest clients, but it still generates a very large amount of upload traffic. On the resource side, on the other hand, the WAN bandwidth is scarce and varying. So to test this, the authors conducted a day-long measurement across 2 EC2 sites, and we can see that the bandwidth that is achieved fluctuates greatly, and it even drops to 25% of the maximum. And similar variations have been reported for wireless networks, broadband, and cellular networks. Now, what happens to the applications when they see this, when the bandwidth becomes insufficient? Now, applications that are built on TCP are ensured complete data delivery. They don't see the packet drops, but the backlog data hurts latency. UTP, on the other hand, can sort of sense data as quickly as possible, but since the application can perceive those packet drops, it leads to, it hurts the accuracy or the fidelity of the application. Now, one could devise some manual policies that change the application behavior. For example, in JetStream, that was a work that appeared in NSTF 14 by Princeton. One could specify the adaptation policies, such as if the bandwidth is insufficient, switch to sending at 75% fidelity, and to 50% if it still remains insufficient. However, as you can see, these policies are often developer heuristics and may lead to suboptimal performance in many cases. Now, one could also optimize for some application-specific heuristics, some application-specific optimizations, but as we'll see next, these application-specific optimizations may not generalize across different applications. So let's take surveillance application as an example. So it detects pedestrians on the streets. So the top figure here shows what the scene looks like at t equal to 0, and they detect a small target in the camera's view, so that is given in the red box here. Now the bottom figure shows what the scene looks like at time t equal to 1, and since the target moves very slowly, there's only a very small difference. Now, a detection in such a sort of application is said to be positive if the intersection over union is larger than 0.5. This is a standard metric used for object detection. And here are some examples of intersection over unions between two bounding boxes. And since the frames here differ very slightly, one can skip the frames in between and still get good IOU values. So the IO values can still be large if frames are skipped in between. So the authors measure the effect of doing so. So instead of sending at 30 frames per second, even if we send at 2 frames per second, one can see that the accuracy remains still very good, but the bandwidth usage decreases significantly. However, if instead of changing the frame rate, the resolution is tuned from say 1080 pixels to say 360 pixels, one can see that the accuracy can deteriorate really fast, although the bandwidth usage also reduces. And this is because the target here is very small, and so the small differences make a big impact on the resolution. So for this application, adapting the frame rate seems to be the more optimal strategy. However, if we look at some other application, for example, an application that detects object on a mobile phone, like in augmented reality, the target becomes large and it's the camera that moves instead of the target now. And we can see that for such applications, adapting the frame rate is bad because the difference across frames is large, but adapting the resolution works better because the targets are large. So this list basically summarizes how the underlying schemes affect different application behaviors, and it basically boils down to this trade-off space between fidelity and freshness. So the horizontal axis here is the data freshness, which is measured as the reverse of the latency. So the more to the right, the better. And the vertical axis here is the data fidelity, which is measured as the application accuracy, and it ranges from 0 to 1. So the options that we discussed in the earlier list are basically design points on this trade-off space. So TCP is on the upper left corner, which can give you very high accuracy, but bad latency. UTP is on the bottom right corner, that gives very low fidelity, but very small latency as well. Manual policies explore this trade-off space, but they can be suboptimal for many cases, and application-specific optimizations can also be suboptimal when the application changes. So in this work, the authors present AWStream that achieves both freshness and fidelity. And this comes from their observation that applications must be adaptive and that adaptation policies must be precise, automatically generated, and targeted for each application. And these policies are what they call Pareto optimal profile that maximizes application accuracy while satisfying the bandwidth requirements and avoiding congestion. So at its core, AWStream proposes systematic and quantitative adaptation that has 3 key parts. First, new programming abstractions to express the adaptation. Second, automatic data-driven profiling. And finally, runtime adaptation. Now the figure here shows these 3 key parts and how developers can use AWStream. And I'll now begin with discussing each of these parts one by one, starting with the developer APIs and the streaming operators. Okay. So the basic building blocks that the application developer can use here are operators that transform an input data stream into a new data stream. Examples of such operators include map that applies some function to each element, or window that groups stream elements together. And these are examples of some normal operators that have been used in prior works before. The new operator that this work introduces is called a maybe operator that is parameterized by k, which is a tunable knob. And this maybe operator basically allows the application developers to provide some hints to the system as to what aspect of the application can be adapted or degraded to support a smaller bandwidth. And on top of this basic maybe operator, they can build a set of other operators that can be used differently by the applications. So as an example of how a maybe operator can be used, so this code snippet shows a quantized data stream where the input could be a stream 1, 2, 3, 4. And then after applying the operator, it can become either 1, 2, 3, 4 if no adaptation or no degradation is applied, or it could be 0, 1, 1, 2 if when k is equal to 2, so you have a degradation level of 2 here, or it could be 0, 0, 0, 1, 1 and so on when k is equal to 4. And with such maybe APIs, the original pedestrian detection application can be expressed as shown. So here there are two maybe operations that are used: downsample that can reduce the resolution, and skip frames that can reduce the frames per second. Now, the next step after this application has been developed is to profile it. So for this, the authors take a data-driven approach by feeding the training data and providing accuracy measurements. And they learn the effect of each degradation operation as shown by this table. So each row in this table depicts a particular configuration of the application depending on how its maybe knob is set. Now the goal of profiling is to learn a Pareto optimal strategy. This is illustrated with this figure. So the x-axis here is the normalized bandwidth and the y-axis is the accuracy. And the authors measure the effect of each configuration. Now, what they're looking for here is the Pareto optimal configuration, which can be mathematically defined by this formula that says that the set of better configurations is an empty set, where a better configuration is the one that requires less bandwidth but offers higher accuracy. And visually, these configurations are marked by these red dots in the figure. So you can see that whenever we move from this red dot, we'll either compromise on the accuracy or we'll use higher bandwidth. Now, once this profile has been learned, once you've learned how every configuration affects the accuracy and how much bandwidth it uses, it can be applied at runtime. So originally, the applications simply transmit data from the source to the server and perform analytics. With AWStream, this is augmented with control flows and system components that perform a feedback control. So the adaptation controller monitors the local queue length and the congestion signals that it receives from the receiver, and it then controls the level of adaptation or the degradation using the maybe operators to better match the available bandwidth. Now, the adaptation algorithm is shown as a state machine here, and it's somewhat similar to TCP adaptation. So they have 4 states: startup, degrade, steady, and probe. So the degrade phase is similar to multiplicative decrease of TCP, while the probe phase is similar to additive increase. So in the degrade phase, they kind of degrade the accuracy such that lower bandwidth is used, and then they try to probe for more bandwidth by sending some dummy traffic. Okay. Now, what is unique about AWStream is that they have a profile that characterizes the application performance, and when adapting, AWStream pinpoints to the right configuration. Now, before moving on, let's quickly discuss the importance of the probing phase. Recall that in the learned Pareto optimal profile, the configurations are discrete. So suppose that the available bandwidth is between 2 configurations. Then without probing, the applications can jump between the 2 configurations. And so basically it starts from one configuration and then jumps over to another. It may demand too much bandwidth, it goes back, and it can keep oscillating between the 2. Probing allows AWStream to ensure that there is actually enough bandwidth before it moves on to the next configuration. Okay. Now the authors built 3 applications on top of AWStream: augmented reality, pedestrian detection, and log analysis that extracts stop K. For the first 2, in addition to resolution and frame rates, they also changed the quantization level, that is a parameter exposed by the video encoder. And for the top K log analysis, some application-specific knobs N and T are used in the maybe operations. Now, their evaluation answers the following questions. First, can AWStream generate accurate profiles across multiple dimensions? Next, can AWStream profile efficiently and support online profiling? Can AWStream runtime improve data freshness and fidelity when facing insufficient bandwidth? And finally, can the profiles generated be used to guide bandwidth allocations among multiple applications? In the interest of time, I'll only be discussing the first and the third questions that they evaluate, and the rest of the details can be found in the paper. So first, we'll look at the generated profiles. Now the figure here shows the bandwidth on the x-axis and the accuracy on the y-axis. And each cross dot here represents a configuration. So the cross dots are the ones in lighter blue. And they've also highlighted the configurations where only a single dimension is tuned. So for example, the red points here show the configuration as the resolution is tuned. The yellow line here is how the configuration changes as the frame rate is tuned, and so on. And the Pareto optimal configuration is shown as the darker blue dots. So they compare pedestrian detection with augmented reality side by side, the different configurations generated by these. And a lot of interesting observations can be drawn from these graphs. First, the optimal strategies need a combination of all dimensions. So you can see that the Pareto optimal configuration here is not obtained by just tuning one dimension. It's actually a combination of multiple dimensions. And second, for the same applications, different dimensions can have different impacts. And third, for different applications, same dimension can have a different impact. For the top K, the profile quantifies the impact of the parameters N and T. And while these dimensions are not as separated as in the video analytics applications, the profile gives them a good quantitative measurement that can guide adaptation. Okay, so next we'll discuss their runtime evaluation. And they compare AWStream with a few baselines. The first one is streaming over TCP, which is a non-adaptive approach. The second is streaming over UDP, that represents RTP, RTSP-based video streaming. This is followed by JetStream, where they use a particular manual policy excerpt from the paper, which is shown here. Then JetStream++, which is a modified version of JetStream that uses the profiles learned by AWStream, but it still uses the JetStream runtime and does not probe and therefore is prone to oscillations. And they finally compare against HLS, which represents HTTP-based adaptive streaming. Now, the controlled runtime experiment follows JetStream, where they apply traffic shaping at 200 seconds. They increase the level of shaping at 380 seconds and remove shaping around 440 seconds. And the figure here shows the achieved throughput, and they also measure the latency and the accuracy. We can see that TCP, which had queued items when the bandwidth was scarce, tries to catch up when more bandwidth is available. But the latency due to backlog data is very large, so notice the log scale on the y-axis. And while TCP gets good accuracy, UDP, on the other hand, has a pretty bad accuracy, even though its latency is very small. For JetStream, it can balance latency and accuracy better than TCP, but it cannot sustain severe bandwidth shaping because of the specific manual policy that it uses, and so its latency grows. JetStream++ uses the learned profile that AWStream uses, and while it provides better bounds on the latency, it reacts to bandwidth changes too quickly and suffers from policy oscillations because of the lack of the probing phase. For HLS, it is adaptive, but there is a fixed high latency due to its chunking behavior and the use of large receiver buffer. Finally, AWStream, which is the system, achieves both low latency and high accuracy at the same time. So the performance numbers from before have been summarized in these box plots for clearer comparison. And when we combine these two figures, we get back to the figure that was discussed earlier in the introduction, where they show how AWStream achieves both fidelity and freshness at the same time, especially when compared to other competing schemes. So basically in this talk, we looked at the emerging wide area streaming analytics that are becoming pervasive with more IoT applications. These applications must address the scarce and varying WAN bandwidth, And in this talk, we discussed AWStream, which is a systematic and quantitative approach that includes novel APIs, automatic profiling, and runtime adaptation. Okay, so now if you have any simple questions, I can try to answer them. But if you want more accurate answers, it might be better if you contact Ben directly. Thank you.
Any clarifying questions for Radhika?
Okay, good.
Thank you,
Thank
Radhika.
you.
Thanks very much. Okay, our next speaker is Siddhartha Sen from Microsoft Research. Siddhartha is going to be telling us about Chameleon video analytics at scale via adaptive configurations and cross-camera correlations.
Okay. Okay. Put this up here. Oh, it's good. Okay, sorry. Shouldn't have touched that, I guess. Okay, thanks. So today I'm going to talk about Chameleon, which is a system for doing adaptive video analytics in a scalable way. This is joint work with colleagues at Microsoft Research, Berkeley, and the University of Chicago. And like the previous speaker, I'm actually representing Junchen Jiang, who was my postdoc at MSR NYC, where we're growing a small systems group. He's a professor at University of Chicago now, and he wasn't able to make it because of visa issues, which, as you know, in the US have become increasingly common since, well, you know. So this is the credit to this talk, and it's really a testament to Junchen's work. He did a great job during his postdoc, and I think he has a bright career ahead of him. Okay, so cameras and video analysis applications are pervasive. We know that. We saw that in the last talk. They're used in things like traffic control. In surveillance, the CCTV cameras in some cities are just amazing at what they're able to do in fighting crime or finding culprits. They're also used in factory floors to make sure health and safety compliance is adhered to. So this talk really is about these kinds of video analytics applications. So let's look at some current trends in video analytics these days. So there is this quest towards getting higher accuracy. So think about the traffic control problem where you're trying to detect these objects or these cars on the street. So there's this quest to try to get higher and higher accuracy, but this comes with a higher cost. So you can see this in recent, if you look at the trend of neural networks used to classify images, you can see that as the accuracy or the error of the neural networks goes lower and lower, the cost, the amount of GPU processing you do per frame just keeps going higher and higher. Okay, so there's this tension between accuracy and cost. There's another trend, which is that there's just a lot more cameras. The number of cameras is exploding, the amount of video content is exploding, and so what the community is trying to do is to achieve high accuracy and low cost video analytics applications, but do this in a way that can scale to the sheer number of cameras and video content out there. Okay, so for the purpose of this talk, I want you to think of accuracy. Think about the traffic analytics, the traffic control problem. Think of accuracy as object detection, so it's some combination of precision and recall, which you can combine in something called an F1 score. And for cost, we're going to focus on GPU processing time. Now, everything I'm going to present can work with different kinds of accuracy and cost metrics, but this is what we used in our paper and our work so far. Okay, so prior work has largely approached this problem of balancing accuracy and cost by trying to customize the video pipeline to the video content. Okay? So why is this possible? Well, video analytics pipelines have a lot of configuration knobs, and we saw some of those in the last talk. So this is a typical pipeline. You have frames of video getting fed into this module that resizes them and chooses which frames to sample, and then it's fed into some neural network object detection software. Right? So you can see there are a bunch of knobs you can tweak. The resolution, the frame rate, you can even change which object detection models you're using. And prior work has exploited these knobs to try to customize the pipelines to the video. For example, VideoStorm will do some profiling at the beginning of the video to choose the right configuration parameters for their needs. or works like NoScope, and there are a bunch of other works too, try to create customized neural networks that work for specific kinds of video, so they're more cost effective because they have, let's say, a simpler task. Let's see an example. So this is actually a video from Chameleon, from our system. We'll see an example of why changing a configuration parameter can help. So here are two videos. Well, actually, they're the same video, but on the left, we're going to use a high frame rate, and on the right, we're going to use a low frame rate. And we're going to look at the accuracy of the analytics pipeline, these configurations over time. So if I play this video, you'll see that the accuracy of both the lower and higher frame rate for this particular period of time is roughly the same. Okay, so obviously you'd use a lower frame rate. Nothing much is going on in this video. The lower sampled frame rate is sufficient. But there's a problem because the best configuration does depend on the content you're looking at. So if we continue this video from 10 seconds onwards, we'll see there are a couple of cars that come zooming by, and you'll see that the low frame rate configuration starts to do a little worse, and then eventually it'll recover when things quiesce again. Okay, so this leads to our key observation, which is that video content varies substantially over time, and this means that the best configuration to use also varies over time. And it's not just the frame rate. There are other configuration knobs for which we see the same kind of effect. Resolution, the underlying neural network classifier that you're using, other knobs as well. So prior work largely has done one-time profiling at the beginning of a video query or a video feed and use that configuration throughout the remainder of the video. So what we're advocating instead is to do periodic reprofiling. Okay, so instead of the prior approach of customizing the video pipeline to the video content, we think of this more as adapting the video pipeline to dynamic video content. Okay? So what do we mean architecturally? So you have this pipeline here, and Chameleon is basically going to sit in this continuous loop and periodically reprofile the video content and tell you what knob values to use. Okay, it's going to continuously do this. So now this is obviously not going to be easy, otherwise I wouldn't be presenting anything, but let's look at the potential win. Let's look at the good news first, and then we'll see what the bad news is. So what is the potential win of doing periodic reprofiling? So here's a plot of cost on the y-axis and accuracy on the x-axis. And in blue, we have the prior work. Basically, when you do one-time profiling at the beginning, this is kind of what your cost accuracy trade-off looks like. There are a bunch of videos in this data set, like 120, so that's why there are that many points. Now, instead of doing a one-time profiling, if you did periodic profiling, you get the red dots, okay? That's like, you're getting very good accuracy and you're getting better cost because you're actually changing the configuration you're doing periodically. So there's a high potential win there. The thing that I'm hiding here is the cost of doing the reprofiling, okay? So we ignored that here. If you include that cost, this is what it looks like. So basically, you lose all the gains you get. Okay? Notice that y is a log scale. So the yellow dots show you that, if you're going to periodically reprofile the video at a rate that is good enough, the amount of cost you incur basically negates any potential gains you'll get overall. Okay? So the key challenge we're going to face is how we're going to reduce this reprofiling cost. I'm telling you to reprofile periodically, but it's super costly. How are we going to deal with that? So that's the problem setup. And we're going to basically reduce the profiling cost using 3 ideas. Okay? The first is exploiting temporal correlation within videos, within video feeds. The second is to exploit what we're calling spatial correlation, or cross-camera correlation across video feeds. And the third is to exploit the independence of these configuration knobs. Okay? I'm going to focus on the first 2 and very briefly touch on the third. I really want you to remember the idea of temporal correlation and spatial correlation, because I think those ideas kind of transcend the particular application that we're using, that we used in our paper. Okay, so let's get right to these ideas. So what do I mean by temporal correlation? It's a very simple insight, which is that the underlying characteristics of a video remain stable for short periods of time. So think about things like the size or the class of the objects or the viewing angle of your camera. And so what this means is that configurations that are good tend to remain good for some time, and configurations that are bad tend to remain bad. So as an example, we can look at our demo video, right, where this is what it looks like at 0 seconds, and then this is what it looks like at 10 seconds. And throughout this process, not much has changed. Okay? So you can imagine that a good configuration that you picked in the beginning would probably do fine for those first 10 seconds. Okay? So that's the temporal correlation idea, very simple. Now, what is the spatial correlation idea? So this is looking across cameras. So our insight is that many camera feeds actually share very similar characteristics. So think about traffic cameras deployed in a city. They'll see similar vehicles, similar weather. They'll also see similar viewing angles because you have these uniform camera installation policies, right? People, like the city mandates that they're installed in a certain way, and so this actually works to our advantage. And as you proliferate more and more of these cameras, you're gonna have more and more cameras that are similar. So what this means is that good and bad configurations that you find for one camera will tend to be good and bad for other similar cameras. Now, there is this problem of how do you find these groups of related cameras in the first place. I'm not going to talk about that. You can look at our paper. But right now, we use a very simple clustering solution when we do this offline very infrequently, and it seems to work okay. It should be improved, though. And I'll mention that a little later in our evaluation. Okay, but assume that you got these groups of cameras that are related. So here's an example of related cameras. So the top two are cameras at intersections, traffic cameras at intersections from our traffic data set. And there are different intersections, but they look kind of similar. The bottom two are cameras from our indoor cafeteria data set. And they're also different cameras, but again, they also look a little similar. So let's look at the top two cameras. So if we take the top two video feeds, and we take some random configuration for the video analytics pipeline and run it on both feeds, we'll find that the cost accuracy trade-off is pretty well aligned. You can see the lines almost overlap. If we take a different camera in this data set that's like a little further away in the city, different location, we'll see that its cost accuracy profile is quite different. So camera 1 and 2 are part of the same group. Camera 3, not part of that group. Okay? So there are some caveats to these two ideas that I mentioned. You can't just take the best configuration and apply it temporarily across your video or spatially across multiple cameras, because the best configuration tends to be unstable. Think of it like you would never use the max for something. Like the max is a very stable quantity. But instead, if you look at the top K configurations, that's a lot more stable. Also, these ideas, these correlations don't hold indefinitely. So you have to once in a while, like periodically, explore the full configuration space, because the top K best configurations may fall from grace. They may become bad, and some configurations that were not in the top K may come into the top K. So you need to do this periodically. All right, so let's put the ideas together, and this is essentially what Chameleon does. So I think this slide and this picture, if you want to remember what Chameleon does, summarizes it well. So let's say we have a bunch of cameras, and I'm just going to arbitrarily pick one of them as a leader and the others as followers. They're part of the same group, so they're similar cameras. So what most work does, almost all prior work, looks at a profiling window, and they'll say, okay, we'll profile for this amount of time, we'll get the best configuration that balances whatever objectives we have, and we'll use that configuration from here on. So essentially, their profiling cost looks like this blue box, because they have to do it for the entire profiling window, and they have to do it for each video camera separately. So we're going to try to whack at that blue box and get the cost down. So the first idea is temporal correlation. Let's apply that. So in order to do this, we're going to take that profiling window and split it up into segments, okay? And then we're going to profile only at the beginning segment of each window. Okay, so we did this full profiling at the beginning of each window. And what we're going to do is we're going to take the top K configurations from that and pass them on to the next segment, so that the subsequent segments only have to do very, very lightweight profiling on just these top K configurations. And then we can carry that through to the remaining segments. Okay? And you can do this for every camera. So we've basically taken the big blue box of profiling cost and shrunk it down to these six dots, these six big blue dots. Okay, so that's a significant reduction. But as you can see, one thing we're not taking advantage of is the cross-camera correlations here. So we can do that too. So now, instead of doing the same thing for each camera separately, we'll take the top K configurations from the leader camera and pass them on to the follower cameras. Okay? And then the follower cameras can then apply temporal correlation to carry it through over time. Okay, so we've taken this big blue box and reduced it to basically one profiling per segment per group of cameras, which is a substantial reduction. Now this blue dot is itself still a pain, because it's a full configuration space profiling, and this configuration space is fundamentally exponential. So this is where our third idea comes in, and basically what it's going to do is it's going to reduce the cost of a single profiling event, a single blue dot. Okay, and this includes coming up with the ground truth, which, like a lot of work in this area, we use a more expensive golden configuration to decide what the actual truth is, and then we can compare the configurations we're trying to this ground truth. So you need to do all this stuff, and it's described in the paper. But at a high level, what we're doing is we're leveraging the fact that the knobs largely look independent, and they exhibit monotonic performance properties as the value of the knob increases. And we're going to basically use these ideas to reduce the search cost from something that's exponential to something that's linear. Okay, so let me show you some performance evaluations. So we looked at 2 different data sets. We tried to generalize these ideas because we did feel that they were general, but there's more work to do in generalizing it. We did look at 2 data sets. One is from 5 traffic video cameras in Bellevue, and another is from 10 cameras in an indoor cafeteria. We also looked at 2 different video analytics pipelines that have been used in the literature and in practice. The first pipeline takes raw frames and first samples and resizes them, and then puts them in an object detection model. The second one takes these raw frames and identifies regions of interest first, where the objects live, and then directly sends them to a neural network classifier. And the same neural network classifiers, by the way, are used in the object detection model software. So slightly different, but both used. And we also experimented with different kinds of accuracy metrics. So label-based accuracy, which is a bit of an easier metric, where you're just trying, when you detect an object, you're just trying to see if it matches any other object from your ground truth that has the same label. And the bounding box-based one is more restrictive, where you have to match the object as well as a location on the video frame. So all the results I'm going to show you, I believe, are from the bounding box-based accuracy, so the harder metric to satisfy, the harder accuracy metric to satisfy. Okay, so Chameleon overall improves both cost and accuracy. This is on the traffic video dataset. There are a bunch of graphs in our paper that basically look like this. I took one of them. It's comparing the one-time profiling approach, which represents prior work, with Chameleon, which is doing the periodic reprofiling and using all these ideas to cut down that profiling cost. So you can see that we're getting better accuracy, we're maintaining cost, or we're reducing cost as well. So it allows us to make claims like we can give you 20 to 50% higher accuracy while keeping costs the same. Or if you want to reduce cost, we can give you the same accuracy while reducing cost to 30 or 50% of your original cost, which is like a 2 to 3x speed up. So this is good. The results also generalize through different pipelines. Well, the different pipeline, because we had 2 pipelines. So this is the second pipeline, and this is an example plot from here. And you can see that, in this case, there's a bit of a Pareto optimal effect going on here. We are increasing cost slightly, but we're improving accuracy by quite a bit. So this is the second pipeline that I mentioned. We also tried applying Chameleon to a different data set. And I'm showing it in a different way here, but this is the cafeteria data set. And A, B, and C, and D here represent different groups of cameras, okay? And I just want you to look at these numbers. So groups A, C, and D, those groups, we were able to improve cost by a significant amount, okay, while maintaining accuracy. And in the last group, we reduced cost by a little bit, but the bigger deal was that we improved accuracy by a substantial amount. So Chameleon, it helps in both ways. It sometimes will help you with cost, sometimes with accuracy, and sometimes both. I wanted to highlight the benefit of using multiple cameras, because we think that this is an important idea, this cross-camera correlation idea. So here's a graph that shows, again, cost versus accuracy, but it starts off with using one camera in a group and increasing the number of cameras in the group. I'm showing 2 lines here because the bottom line is just the cost of running your configuration. The top line includes the cost of profiling. And the point here is that adding more cameras reduces the profiling cost linearly in the number of cameras, whereas it doesn't really affect the cost of executing the best configuration, because by then you're done with all your profiling. So you can see that if you increase the number of cameras, you get this pseudo-linear drop. And that's going from 1 camera to 2 cameras. And then as you keep going further and further to 7, 8, 9, 10 cameras on the left, cost is going down in a semi-linear way. Now, notice that our accuracy also dropped. But look at the y-axis, right? It's going from 0.78 to 0.71. So accuracy didn't drop too much, but it did drop. And the main reason for this is our grouping algorithm. At least that's what we believe. It's very naive, and it includes multiple cameras that they're not as similar as we would like. So there's definitely a lot of work that can be done if we use fancier grouping algorithms. Okay. I also wanted to give you an idea of how much each idea that we used actually affects our results. So this is a plot, again, of cost versus accuracy, showing what would happen if you did the periodic reprofiling that we're advocating, but did an exhaustive search each time. Okay, so initially your cost is very high. Now, if you apply temporal correlations, it'll drop to this amount. And then if you apply the spatial correlation idea on top of that, it'll drop even further. And then finally, if you use the entire Chameleon solution, which uses the independence of configuration idea, the third idea, it drops to something like this. Okay, so all of these ideas, the three main ideas we used in our paper, have a substantial effect on performance. Okay, so that's it. So what we've seen is, a general proliferation and trend in the number of cameras and video analysis applications out there. And I think this really calls for a need for video analytics systems that scale. The main observation of our work is that video analytics pipelines must adapt over time because the video content changes over time. And the key insight we had was that video feeds exhibit both temporal and cross-camera correlations that can be exploited. And so this led directly to our technical contributions, which are essentially these techniques for cutting down the cost of reprofiling your video analytics pipeline periodically. And when you do all this, the result you get is that you can get substantially better accuracy at a similar cost, or vice versa, or in some cases improve both dimensions. Okay, thanks.
Questions for Siddhartha?
I will also try hard to answer your questions.
Hi, Arseny Zastronych from EPFL. This is a very interesting number of insights. One thing was bothering me though, when you group the cameras, they may be similar in similar situations, similar view angles, the same type of land, but at the same time they may experience very different situations, like a busy intersection, a collision on an intersection, a rush hour in a cafe. And so that would require a different top K set of configurations. How do you take this into account?
So I think that, the first thing to remember is that, even though they will experience different effects, they're still related to each other and in the same group. And I think the way we handle that is basically by doing the reprofiling periodically enough. Like we show that you need to pick a time scale for your profiling window such that these top K configurations all appear in that window and they're all useful for that kind of time scale. Then when you reprofile, you'll produce a new set of top K. So I agree with you that it is an issue, but I think over the time scales that we're looking at, you're looking at, let's say, 10 seconds or something like that, you'll see traffic flow in a certain direction, and it'll also flow out, and it'll flow to the next camera at the next intersection in the same kind of way, right? So I think if you use a large enough time window, a large enough reprofiling window, you will get all these configurations within your top K set. Okay.
Thank you.
So basically, don't use a window that's too small, and again, because you will suffer from the problem that you're saying, and don't use a window that's too big because then you won't be able to adapt frequently enough.
I was mostly referring to different cameras being in the same group, but experience different.
Yeah, I think that's part of what I'm saying. Like, they're different cameras that they're spread out, so they see different time effects. But if your window is large enough, you might be able to include the configurations that apply to both kinds of the slow and the fast times.
All right, thank you.
I have simple questions. I understand the cost is important.
Right.
My question is why the GPU cost is the most important.
Yeah.
What about other costs?
So I think that other costs certainly are relevant. We saw bandwidth in, I think, the last talk, and we haven't considered, for example, something like network bandwidth, and there are other costs to consider. We focused on GPU processing because we were looking at the analytics pipeline and the neural network processing underneath it, and the primary resource, the most expensive one, at least when we were trying to run all our stuff, was this GPU processing. So we did focus on that. I do think that you can apply this work to other kind of cost metrics. But that is just the one we chose. I agree that there are other cost metrics and we should look at them. For example, I think network bandwidth is an important one when you think about these edge cameras and how they communicate video to the data centers where you're doing your analysis.
Hi, Hari Balakrishnan from MIT. So I have a question about how you know if you're in a bad configuration. How do you actually, what in the system makes it understand that it's in bad configuration? In particular, a use case you mentioned before was finding these rare events like a culprit, or you're searching for a particular type of vehicle or something like that. So I get the idea of one architecture where you push the models down to the cameras themselves and they're processing everything, but that's not actually what you're talking about. So if you see a rare event and you're running at a frame rate and you're missing it, what in the system pushes it toward getting accuracy back? And I don't think your metric captures that, because your metric is much more about looking for a set of labeled images, labeled objects and images.
Yeah, so so the way we compare the performance of a configuration is by comparing it to some kind of ground truth that is being run on all the frames of the video. So there is that, we have that. We can have the ground truth and our configuration and find that it is not capturing or finding the objects that are actually happening there. That could be used. But that said, I think that there is, I don't think I can confidently say if we haven't really tried our approach on like that kind of anomaly detection that you're describing. So I think we have to rely on the ground truth. If the ground truth is showing us that these objects actually did exist and we found this particular person and our configuration is not finding it, then that mismatch will be an indicator to Chameleon that we need to do something and we need to reprofile.
I guess my more broader question is, if you're looking for needles in a haystack,
Yeah.
like something that shows up once in every 1,000 or 10,000 images in the whole
You might miss
system,
it.
would you actually have a different design that essentially requires you to run the processing on the actual edge nodes or the devices themselves? Or do you actually think you can do it in the cloud?
I think we need some combination, and we haven't explored the kind of edge-cloud divide and how you would split the responsibilities. I think you would need some combination. You need to do some fast stuff at the edge with its limited processing and resources available there, and then do some other stuff in the cloud. I also think the cloud can be used to do kind of backwards work. It'll be at a lag or at a delay, but it can probably do some backwards work to catch up with something. Let's say if the edge detects that something weird happened, but you can't keep doing that because then you'll just keep falling further and further behind. But we haven't, so this is one of our future directions, which is to figure out how to balance this kind of the edge processing with the cloud, and maybe that can help deal with the kind of situation you're describing.
Thanks.
Yeah. Please.
Hi, I'm Shripriya from University of Göttingen. Well, I had a similar question, but that was already answered. But the other question I have is, how do you decide your profiling window? Is it static throughout the profiling time, or is it dynamic? Because,
That's a great question. I think, for what you've seen here, we've tried different profiling windows on the data sets we had, and we've basically stuck to a static one. But we haven't really spent much time figuring out how you would kind of dynamically adapt this profiling window. I think there are different ways you could do it, and I think that would orthogonally help our work in general, but it's a good question. I can imagine certain things, and I can give you ideas for how to do it, but I would say that we don't have results showing kind of dynamic adaptation of the profiling window right now.
I have just another small
sure.
question then. Since you have a static profiling window, and now you already have this profiling parameters that you're doing for the beginning of every window, what is the actual difference? And you have the sample, the top K, the smaller sample, right? And then you do again another complete profiling for the next window. So how much difference did you actually see in the change in the top K parameters between the previous smaller top K and the next top K that you actually did?
Oh, there was change, yes.
Yeah.
So I don't have the exact numbers of how it changed, but that's a good metric to look at. And it would change. I mean, we tried different profiling windows.
Right.
Even though we didn't do this automatically and dynamically, we did try different ones. And we found a sweet spot that worked for that class of data that we were looking at, the traffic data, the cafeteria data. And it would change quite a bit. And the re-ranking changes too. So remember, in each segment, you're taking the top K and also you're doing some work on them. So you are re-ranking and reprofiling them, and that ranking does change at even the segment time scale, in addition to the profiling window. So yeah.
Okay, thank you.
All right, thanks, Siddhartha. Okay, so our next speaker is Mingmin Zhao. Mingmin is a third-year PhD student at MIT working with Dina Katabi, and he's going to be telling us about seeing 3D skeletons using RF signals.
Thanks, Mohammad, for the introduction. Hello, everyone. I'm Mingmin. Today, I'll be telling you how we can see human skeletons through walls using RF signals. This is joint work with my colleagues from MIT. I'm sure many of you have read about Superman when you were kids, and I particularly was so fond of Superman when I was a kid. There were so many days when I was staring at the wall and trying to see if I can focus on it and start seeing behind it. Of course, I didn't succeed, but I hope by the end of the talk today, Superman would either be proud of me or jealous of me. So many researchers have also been looking at this problem. They have been trying to see whether they can develop a device that can see through walls. In particular, about 15 years ago, DARPA has funded a project that tries to see through wall. And this is the resulting device. It can tell whether it's a person standing behind the wall. Later, around 2011, there was another big jump from MIT Lincoln Lab, where they created a device that can further localize the people when they are moving behind the wall. However, as you can see, this device is so huge that I have to move it on a truck. Later in 2013, and actually at SIGCOMM, we saw a paper presented that was able to use very low power consumer devices to be able to track human motion behind the wall. And they can do this with much smaller devices. Now let's just go over how this kind of system works. The idea at the high level is very simple. You have an antenna array that transmit wireless signals. As we know, those wireless signals can traverse through walls. And they also reflect off human body because our body is full of water. The reflection will finally come back towards the device. The job of this device is to use the propagation time of the signal to try to detect a person or localize him. And they will give you as output a dot on the floor. If the second person in the environment, they might give you a second dot. Of course, this is major advancement in terms of seeing behind wall, but this is really not satisfying, because when I want to see through wall when I was a child, I want to see the same thing as a Superman. I want to be able to tell whether this person is standing, is sitting, or what he's doing. I don't want to just see a dot. So the idea that motivated us is, can we just go from a dot to a full human skeleton, a dynamic skeleton that is moving with the person behind the wall? I'll start by showing you some of our results, and then I'll come back and tell you how we did it. So the video I'm gonna play right now is the output 3D skeleton from our system. In the corner, you will be able to see what's happening from a camera's perspective. You can now see how people are moving based on our skeleton, and you can tell whether they are sitting or standing. You have an idea of what's going on. You can also have more people, and our system will still work. You will be able to tell from our skeleton whether this person is taking a left step or taking a right step. And of course, all of this is from behind the wall. So now I have showed you our result, but how do we do it? How can we get a dynamic skeleton from RF signals? One way to try to solve this problem is try to go and model human body, model how humans have arms and legs and all those different parts move and how RF signal is gonna be reflected from them. However, I have no idea whether this method would work, but if you're gonna do it this way, this is gonna be very, very difficult. What we did is to use neural networks. Neural networks have recently shown that they are capable of abstracting very complex systems and dynamics. Without you telling them exactly the model, they will be able to learn it from the examples you provided to them. So it's natural to ask ourselves this question, since we're facing this very complex system. Can we use a neural network to help? In the rest of this talk, I'm gonna tell you the details of our system, RFPost 3D, which, as I said before, is based on neural network. However, you cannot simply use neural network to work with RF signals. That is very different from images or videos. So I'm gonna start by telling you what is the difference and the challenges when you want to use neural network to process RF signals. And then I'm gonna tell you how we solve these challenges and design our model. Finally, I want to show you more quantitative evaluation results of our system and tell you when it works and when it doesn't. Okay, let's start. Before getting into the details, it's very important to make sure that we all understand this problem. The problem statement is that we're going to take an RF signal and try to spit out the skeleton. But what does it mean by spitting out the skeleton? It means effectively we are spitting out the exact 3D location of key points of human body. A key point is something like your head, your leg, your shoulders, and your elbows. A skeleton is all of those key points as opposed to a single dot you would get in the old systems. So now we have understand this problem. Why can't we just do neural networks, which has been very successful with images and audios to the RF signals that we want to work on? The first challenge is something we call specularity of human body with respect to RF signals. Let me explain to you what I mean by this. I'm going to show you a very simple example. You can see here we have antenna array and a simple reflector. When you transmit RF signals, they're going to shine on the reflector. The part of the signal that falls along the normal to the surface will reflect back towards the device. However, if the signal falls onto a different part that is further away from the device, the reflection will deflect from the device. Effectively, this means that the antenna array is only getting the reflection from a small portion of this surface. It's not seeing the whole reflector, but just a small part of it. So what does that mean for human body, as opposed to this simple reflector here? Let's take another example with human body. Again, the signal is shining on the surface of human body, but only a small percent of that signal is reflecting back towards the device. In this example, only the signal falls on the left forearm of this person is reflected back towards the device. The rest of the reflection from the head, from the chest, for example, is just deflecting away. So the antenna array is not going to see the human body, but just a small part of it. This is very different from images, where a single snapshot would capture the whole human body. Here, a single snapshot of RF signal would only capture a small subset of human body. To solve this challenge, the first idea of our solution is to use human motion across time. As human moves, different body parts would reflect signal back towards the device. In this case, for example, the chest is reflecting. Therefore, to be able to capture the whole human skeleton, we have to use a series of RF signals. Some of them may contain arm, some of them may have reflection from your chest or your leg. But the problem is that all these body parts, they do not belong to the same snapshot. Simply stitching them all together wouldn't give you a dynamic skeleton that is changing over time. So what we want to do is a bit more complicated than this. We want to give multiple snapshots to the neural network and teach it not only to generate body parts that is visible in each snapshot, but also to fill up the missing body parts in every snapshot. With that, we can get a full dynamic skeleton. Are we done? Unfortunately, no. Let me tell you the reason. The snapshot I'm showing you here is actually a simplified version of reality. In reality, each RF snapshot is actually a 3D functional space, because typically you're using antenna arrays to capture reflections from different points in the 3D space. Therefore, when we're looking at a series of RF snapshots, we're really looking at the 4D function of both space and time. The problem with such 4D RF signals is that they are too huge for neural networks. Neural network tools nowadays deals with 2D images or 3D videos. They don't naturally scale to 4D inputs. Not to mention all the space and time complexity you have to deal with when you're training such a model. So what should we do? So here's our solution. We decompose the neural network. Specifically, we model RF signals and RF systems, and we prove that in the paper, for the RF-based 4D neural networks, we can decompose it into a combination of two 3D neural networks. 3D neural networks is something you would use when you're dealing with videos. They work with standard libraries, and they run relatively fast. What this theorem is telling us is that we can achieve effectively a 220 times speed up in training our model. A model that would originally take 1 year to train can now be trained within 2 days. But for the model to be able to work well, we have to solve the second challenge, which is complexity. Let me explain to you what I mean by complexity. We've talked about RF signal being reflected from human body, and that's what we're using to estimate human skeleton. However, RF signals not only reflect from human body, it also reflects of everything in the environment, the walls, the tables, the chairs, everything. Those reflections will also be different from one environment to another. But notice that all those reflections from objects in the environment, they're irrelevant to the problem of interest, which is to discover the human skeleton. So you want to remove those extraneous information. The second thing is that there might be unknown number of people in the environment. There might be cases you have one person, no person, or multiple people in the environment. So now you have extraneous information from objects in the environment, and you have to deal with unknown number of people. If you ask a single neural network to do all of these things, in addition to learning the human skeleton, that's just too much. It means that this neural network has to be huge. As we all know, training a neural network already requires a huge amount of data. But if you ask a model to do all those things, you're just going to need a humongous amount of data. And this model is going to be very hard to train, even if you are able to get all those data in the first place. So how can we solve this problem? Our solution is task separation. Instead of asking the neural network to do everything at one shot, let's separate the task and have neural network to do things in 2 steps. So we can first have a neural network whose job is to zoom in on different people, removing everything else. So this first neural network, it just needs to output boxes centered around each person in the environment. Then the second neural network just needs to take into those boxes and zoom in on them to extract a human skeleton. Interestingly, by zooming into the regions that have people, our model eliminates all the extraneous information from the environment. Also, by presenting the second neural network a single box at a time, it just needs to estimate its skeleton from a single person. It doesn't need to understand how many people are there and how they are with respect to each other. With this task separation, our system becomes much easier to train, to scale, and to generalize. So now I have to tell you the design of our neural networks. The last thing we need to do is actually to train it. Usually when you want to train a neural network, you need to show it a large amount of examples. Let's say you want to extract skeletons from images. How would you train your model? So you probably want to go and show an image to a person and ask him to label the skeleton. So he can go and say, this is the head, this is the leg, this is the shoulder, etc. So this is a bit annoying, but it is possible. In fact, this is how most of the vision datasets are created. You just need to go and get a bunch of people and label tens of thousands of those images, and then you can train a model. Let's go and see if we can do the same thing with RF. Imagine if I go and ask someone to label human skeletons from RF signals. This is not even possible. This person might just go crazy. So how can we obtain a large label dataset to train our model? Our idea is to use images to help. The idea is that we can collect synchronized images and RF signals at the same time. And instead of asking the person to label skeleton from RF signals, we can ask him to do it from images. Here's how we're going to do it. We're going to use multiple cameras to capture images of people from different views. We can then ask humans to label skeletons from each of them. We can then solve a geometric optimization problem that brings those 2D skeletons from 2D to the 3D workspace. And this gives us a 3D skeleton label for the corresponding RF signal. What is even better is that we can use state-of-the-art vision algorithm to replace human. We can use vision-based neural network to extract 2D skeletons from images. Due to the reason developed in vision, those models actually works very well, almost as good as human annotators. So now we don't even need to annotate a single image. This enables us to collect a huge amount of data in a short period of time. And of course, those cameras are no longer needed once we train the model. Now let me show you the evaluation of our system. Let's first look at how we implement our system. Our hardware is similar to past work on indoor localization. It uses FMCW radio with antenna array. We implement our model and the decomposition, as we discussed, in PyTorch. To train our model, we collected 16 hours of data from 22 different locations around our campus. During the experiment, people were going about their own life without much interference from our side. So we split the data from those 22 locations and used 16 of them for training and the rest 6 for testing. We did this to make sure that our model can generalize to new environments. It takes our model around 2 days to train with 4 GPUs. To evaluate our system, the first question we want to ask is, how accurate is our skeleton? To evaluate the accuracy of our skeleton, we look at the localization error of each key point in the 3D space. We compare the predicted 3D skeleton with the ground truth and compute the localization error for each body key point. And here's the result. Our localization error is around 4.3 centimeter for the head, and it's less than 4 centimeter for the neck. Our model also works well for the rest of the key points, and even in the worst case, our localization error is less than 6 centimeter. As you can see, our model is most accurate for the key points that is on the human body trunk. For example, the neck and the hip. This is because the large size of the body trunk, and there's more reflection from there. On the other hand, our model is less accurate for the wrist and the ankles, and there's less reflections from them. Our average localization error is around 4 centimeter across all different body key points. This is much better comparing with the error in previous localization system. And also, those systems only gives you a single dot, where we gives you a full human skeleton. Let's now look at the skeleton accuracy with different number of people. The error, of course, goes up when there are more people in the environment. But as you can see, the error is still less than 6 centimeter, even when there are up to 5 people in the environment. The next question we want to ask is, when will this model fail? Let's first summarize the cases when our model works well. It works well through walls and occlusions, because our signals can traverse through walls. It also works well when dealing with daily activities like walking, sitting, having a discussion, or waving hands. Now let's look at the cases when our model will fail. The first type of failure mode is due to someone being static for so long. In this case, for example, there are 2 people sitting in the chairs, but our model is only output skeleton for one of them. This is because the second person has been sitting there for so long that our model started thinking he's just part of the background and decided not to output the skeleton for him. To solve this problem, it will require a new design of a model to take longer history window into consideration. The second type of failure mode is due to the posture we don't even see in the training data. For example, this person is jumping in the air, but our model still thinks he's standing on the floor. As I said, we collected our data around our campus, inside the campus buildings, and we don't see any of those jumping examples. If we want our model to deal with such cases, it will require us to collect more data, including those examples. Finally, we have made a simplified version of our model that is able to run in real time on a laptop. We're going to show a real-time demo of our system this afternoon. If you're interested to see how it works and try it yourself, please stop by between 2 p.m. and 4 p.m. this afternoon at the Northern Hall at the back of this stage. With that, I'm happy to take any questions.
Questions, please.
Hi, this is Xiao from Yale. Very nice work. So regarding the scenario when it will fail, so are you saying that basically you can only do the skeleton for moving objects? You cannot do it for static objects. So, but what if I want to see through the wall, seeing not only the people there, but also what's the potential objects there? Is there a way to do that, or are you aware of any related work doing that?
So the question is being asked is, can our model deal with static object or static person? So on one hand, our model is able to deal with static person. For example, the example I showed you, there are 2 people sitting there, and for one of them, we're still able to capture them. This is because actually our model is trying to fill in up the gap. Even though we're not gonna see his hip, his leg due to that specific posture, but we're still able to infer this information from the motion he takes before he sits down. And on the other hand, for the static objects in the environment, it will be slightly harder if the object is not reflecting the signal back toward the device. But one option to be able to capture those objects is actually to start moving your device, as opposed to have your device static there. So that's one direction for future work.
Okay, yeah. Thanks. Just a quick another question. So to use the image to train your model, so and in your experiment, do you train it with the same participant or just a random person? Does that have any effect on the accuracy?
So as I said, we actually did this experiment, and we didn't see any error because you have new person or new subject. And in fact, during our data collection, we just put it inside our building, and there are a lot of people walking by. Most of the time, the training set and test set, it contains different people. And even when it's different, we don't see any big error because of that.
All right, thank you so much.
Abdul from ETH Zurich. So you mentioned you separate tasks to reduce the effect of noise by zooming. I'm not really understanding what you mean by zooming. Is it like using a directional antenna somehow to cluster the room, or how does that work?
So the question that being asked is, how does the zoom in component work? Actually, our zoom in is not on the hardware side. We zoom in after we process the signal. So once we get the signal in the 3D space, we can zoom in onto a small region. Basically, that region only contains this person or his different parts of his body. And by doing this, we can eliminate reflections from other points in the space.
But then when that person is moving, the object is moving, like the person is moving, right? So if you only zoom...
Mm-hmm. So basically the way we zoom in on different person is also changing over time. We will track this person's location and how his body parts is moving to decide how to zoom in on him over time and over space.
But then you need to know how to track him in the first place then.
Yeah, that's actually one subtask of our model that needs to learn. And we can take this question offline to discuss this.
So another follow-up question. So for the evaluation...
maybe we have only like 2 minutes. Can we move on to the next question and maybe we can ask the next question offline?
Yeah,
please.
Okay, thank you.
This is Moalula from Nokia Bell Labs. Thank you very much. Very interesting work. Just a quick question on the vision annotation. I wanted to clarify, did you use the vision system to annotate the skeleton, or did you use did you use it for training the neural network using domain adaptation or something along these lines?
Yes, we did use neural networks to provide annotations. And those neural net vision models, they only extract 2D skeletons from different images. So what we have to do is augment such systems, and so that we can combine views from multiple cameras and get the 3D skeleton in the 3D space and use it to train our model. And during the training, no domain adaptation is used, because once we get the skeleton, there's really nothing much needs to be
Okay, so it basically
adapted.
was vision annotation for ground truth rather than actually training the radar neural network system.
And it is providing annotation to train the vision, to train the art-based neural network.
I think I got it. Thank you very much.
Thank you.
Okay, I think let's thank Mingmin. Okay, so the final speaker for this session is Sheng Shen. Sheng is a fourth-year PhD student at UIUC, working with Rumit Chowdhury, and he's going to be telling us about using IoT for noise cancellation.
Okay, thanks for the kind introduction. Hello, everyone. My name is Shen Shen, and today I will talk about our project, Mute, where we bring IoT to noise cancellation. So this is a joint work with my colleagues, Nirupam, Junfeng, Haitham, and Ramit, and we are all from the Synergy Group in the University of Illinois, Urbana-Champaign. Disturbing noise is almost everywhere. It can be people talking in your same office, the constructions near the hospitals, the early morning lawnmowers just outside of your bedroom, and of course, the busy streets inside cities. Today's solutions are noise-canceling headphones and earbuds. Their goal is to cancel the sound at your ear. In this paper, we have two goals. One, we want to improve noise cancellation performance, and we show that 9 dB is possible. Two, We want to achieve comparable performance, but we design the headphone in such a way that it does not block your ear. In other words, the headphone is completely hollow. So you might ask, why is that important? Actually, many users find it uncomfortable to wear ear-blocking headphones for long durations, and medical research has shown that it is even harmful. So our system gives users the option to choose between better noise cancellation versus better user comfort. The key idea we bring in to solve this problem is essentially the following. We want to combine wireless networking with conventional noise cancellation. We call our system Mute, and let me tell you the key idea with one simple example. Imagine Alice is reading a book in her office, and she often gets disturbed by the frequent corridor conversations. So Alice decides to put a small IoT device at her office door. This device has a microphone as well as a wireless radio. When the disturbing sound starts, it arrives at this microphone position first. The IoT device will capture the sound waveform through the microphone and immediately forward the sound through its wireless channel. Alice has another device at her ear, which also has the wireless capability. Because wireless signals travel 1,000,000 times faster than sound, Alice's ear device is going to receive the sound waveform from wireless much, much earlier, while the actual sound that is propagating in the air is going to arrive at a much later time. In other words, the ear device gets to know the sound much in advance of the actual sound that arrives later. So the difference in these two propagation delays is what we call look-ahead. This look-ahead time allows the ear device to do all kinds of processing with the sound. So this is the same reason why we see lightning first and hear the thunders later, right? The look-ahead allows us to cover the ear to prepare for the incoming sound, and similarly, it allows mute to cancel the noise at your ear. So today, I will talk about how look-ahead benefits mute in 3 ways. First, it creates a long time buffer for computation, which is necessary for wideband cancellation. 2, it provides future sound samples that are very critical for signal processing. And finally, there are application-specific gains as well. As one example, we should now be able to cancel conversations among multiple humans. Let me start off with the first gain, but before I get into the technical details, let's first zoom into today's noise-canceling headphones and see what is happening inside. So all these headphones essentially have a microphone called the reference microphone, a DSP processor, and a speaker called anti-noise speaker. When the sound starts, it arrives at the reference microphone first. The DSP gets the sound, runs signal processing, computes the anti-noise sound, and sends it to the speaker. So what should this anti-noise signal be? Ideally, it should be exactly the opposite of the noise sound, which is this blue signal, right? But how does the DSP ever know what is this noise signal? It does not. It only has the signal from the reference microphone. So for that, all these headphones also have another microphone called, so the noise and anti-noise will cancel each other, so leading to silence inside human ears. But this DSP does not know what is the anti-noise signal, right? So they put another microphone called the feedback microphone. So this microphone receives both noise and the anti-noise, compute their difference, and send it as the feedback back to the microphone, back to the DSP. So once the DSP now gets the feedback, it knows how to adjust the anti-noise sound until it fully cancels the noise at the ear. So this is how noise-canceling headphones work. Let's look at their performance. We actually measure the performance of the latest Bose QC35 noise-canceling headphone, and here is the result. The x-axis shows the frequency, while y-axis shows the cancellation performance, the quality. So it seems like this active noise cancellation only works at lower frequencies, right? From this graph, it only works below 1 kilohertz. If you start to wonder, why this headphone actually works pretty well when I actually wear it, it is because they have this sound-absorbing material that surrounds your ear and blocks the sound. So this green curve shows the performance after we add the sound-absorbing material to the headphone. So obviously, at these higher frequencies, it is only this material that is really absorbing the sound. So why is this? Why noise cancellation itself doesn't work for higher frequencies? Let's go back to this headphone, but this time, let's look at it from a time perspective. So here is the graph which shows the timeline of this entire process, where time flows in the vertically downward direction. When the noise travels in the air, it arrives at the reference microphone at time t1 and the speaker position at time t2. So the headphone really gets the sound sample, the noise sample at t1, and by time t2, it has to produce the anti-noise sound. So the time budget it has is really t2 minus t1. So how long is this time gap? Well, it is only 30 microseconds because the separation between the reference microphone and the speaker is only 1 centimeter, okay? Divided by speed of sound, that gives 30 microseconds. But within this time budget, the headphone has to sample the sound, run signal processing, compute the anti-noise sound. So all these delays adding up together means the headphone can only produce the anti-noise sound at time t3, which is a little later than time t2. So we talk about many of these details in the paper, but the key message is that now the headphone is running late. It has a time lag, which is t3 minus t2. So you might wonder, what is the consequence with the time lag? Well, for lower frequencies, it is not a big problem, because even if the noise and the anti-noise misalign by a little bit, it is still fine. The error is still small. But for higher frequencies, it is going to be a big issue, because a little time offset translates to a large phase error. This means now you are going to see a large residual error at human ears. So this is one key reason why these noise-canceling headphones does not work well for higher frequencies. Let's now shift the focus to our system, Mute, and see what is the value of having the future sound samples available. So what are we essentially doing? One way to look at our system is to disaggregate the headphones. In other words, we take the microphone out and put it in a separate IoT device further away. Just to give you a rough idea, let's say we push the IoT device 1 meter away. This will translate to 3 milliseconds of look-ahead time, which is 100 times larger than what today's noise-canceling headphones have. As a result, we can easily fit all the processings and all the delays into this time budget, and which means now we do not have any time lag at producing the anti-noise sound. This further means we should now be able to cancel higher frequencies as well. So in summary, simply taking out the microphone and put it somewhere further away immediately gives us the timing gain, which allows for wideband cancellation. But note that we have not really improved the anti-noise signal itself yet, right? So now I'm going to show you how look-ahead can fundamentally improve the anti-noise signal, which leads to better cancellation performance. So recall that what we are doing is essentially we take sound samples from the reference microphone, and in order to cancel the sound at the feedback microphone. But this is not an easy task. It's not as easy as you take the reference signal and you flip it and you are good to go. It's not like that. So the reason is because the two paths along which the sound travels to the two different microphones, they are different. What I mean by that is the sound propagates in the air and gets reflected and distorted in different ways. If we model the first path to the reference microphone as a channel f of x, and we model the second path as a channel g of x, so what does the DSP need to do? It really needs to derive a filter, which is minus f inverse convolved with g, so that now it can translate f of x into minus g of x. So what is this filter, minus f inverse convolved with g? Let's look at this. So if we plot the channel impulse response for this filter, it turns out it relies on both past input as well as future inputs in order to derive the output. In signal processing, this is something called non-causal filtering, and essentially it is because there is an inverse sign inside the filter. So what today's noise cancelling headphones can do is to estimate this filter for the past inputs, for the causal part of the channel. But what mute can do is that it has the look ahead into the future sound, which means it now can enable the non-causal part of the filter, can estimate the non-causal part. So as a result, mute can better estimate this filter, which leads to better anti-noise signal, which further leads to better cancellation performance. So this is the second gain, which is mute can leverage future sound samples to enable non-causal filtering, which leads to better cancellation quality. I'm going to very briefly talk about the third gain, and let me give you one example to show the intuition. Imagine Alice and Bob are in a conversation, and we want to cancel their sound. So initially, when Alice starts talking, our DSP does not know Alice's filter, right? So the error is large at the very beginning. But of course, as the DSP gets more and more of Alice's sound, the error goes smaller and smaller because our filter has converged. But now, once Bob starts talking, whatever the DSP has estimated for Alice is no longer going to work. Now the DSP has to re-estimate the filter for Bob, which means now it has to start from scratch. So of course, the error is large again at the beginning, and again, it goes smaller and smaller as it receives more and more of Bob's sound. So this performance fluctuation happens every time there is a transition between Alice and Bob. So what we can do with the look ahead is that we know what sound is coming even before they actually arrive. So as a result, we can store different filters into our cache, and when we foresee that now it's Bob's sound coming, the sound is going to come very soon, we can prefetch the filter inside the cache, load it on the ear device, and when the Bob sound actually comes, we're able to be ready to cancel the Bob sound. So by doing this prefetching and loading, we're able to cancel Alice's sound and Bob's sound by loading the filters onto our ear device and get fully prepared for the sound. So this is the third benefit, which is we know what sound is coming, and we can better get prepared for that. So having talked about the three gains, let me now show you our implementation and evaluation platform. So here is a human, and we also use loudspeakers for different kinds of noise sources. And we put this IoT relay on the wall of the room. This relay has a microphone and a wireless radio. The job is to capture the sound and forward it through wireless. We designed this entire relay in analog to avoid any possible delay in the forwarding. Once now the sound has been forwarded, we design a wireless receiver near human ears to capture the sound through wireless. We implement our algorithms on the general purpose TI DSP. And here is the feedback microphone on the human head model. And here is the anti-noise speaker. So we call this design mute hollow because we are essentially not putting any sound-absorbing material on the human head, right? So of course, this is a very crude prototype, but we envision that if you design everything well, it should look like the picture on the left, which is a light ear device on your ear, and that is hollow inside. And our goal is to achieve comparable performance as today's noise-canceling headphones that actually blocks your ear. Let's now see the result. So in this graph, the green curve shows the performance of both headphones, while the red curve shows our design, the mute hollow design. And obviously, the performance is pretty comparable. Actually, we are 0.9 dB worse than both on average. So now we want to ask, if we are able to add sound-absorbing material onto our hollow design, then we should be better, right? Because now we are going to have the gain from both look-ahead as well as sound-absorbing material. So how we are going to evaluate that? Well, we actually take the Bose headphone, turn it off, and connect our DSP's audio ports to this headphone. So essentially, we are replacing Bose's algorithm with ours. We call our design on the left mute non-hollow, and we want to achieve better performance than Bose. So this graph shows the result. This purple line is the performance of our non-hollow design, and on average, it is 9 dB better than what Bose can do nowadays. So this is why we said we offer two options to the users. Either you go for better noise canceling performance, or you go to better user comfort. We have many more results in the paper, and I strongly encourage you to read the papers for more details. So to wrapping up, the core idea we are bringing to this solution is that wireless signals travel much faster than sound, providing a valuable look-ahead opportunity to noise cancellation. But what I've shown you is only the tip of the iceberg. We believe this architecture can be generalized in many, many different ways. For example, the first question I'm going to ask is, why do I need to put this IoT relay on the door? I can put it on the table in front of me. Even then, it is fine, because I still get milliseconds of look ahead. That's good enough for noise cancellation. But this gives me portability, because now I can carry this device with me wherever I go and put it on the table in front. So now I ask the second question. I already have this tabletop device in front of me. Do I still need the DSP at my ear? I can move this DSP to this IoT device, and this DSP is going to send anti-noise signal wireless back to me. So now my ear device is going to be more lightweight. Okay, so next, once this IoT device is sending the anti-noise signal to me, why not send it to everyone? In other words, in places such as call centers, where everyone needs noise cancellation, we can put the DSP on the ceiling, and all these IoT relays are shared, so that this DSP computes the personalized anti-noise signal and send it to everyone, as if it is like a Wi-Fi router, enabling noise cancellation as a public service. And finally, this relay can be even on the noise source. For example, if we put the relay on the lawnmower, the relay will immediately forward the sound, and whoever is sleeping nearby can cancel off the sound simply because they have a lot of look ahead, because we put the relay just on the noise source. If you actually step back and look at all these architectures, you might start thinking that wireless is essentially playing the role of a control plane, while the acoustics is a data plane, simply because wireless is much faster than sound. Noise cancellation is one application, but there are many, many others. For example, now we should be able to run real-time machine learning on human ears, because your device gets the sound much earlier before they arrive at your ear. For another example, consider acoustic augmented reality, where the outside sound you hear is augmented by all the processors, because now have adequate time to process the sound before you actually hear it. There are many, many other applications, and I encourage you to read our papers or visit this website for more information. Okay, that's the end of my talk. Thank you very much, and I'm glad to take any questions.
Venkat Padmanabhan from Microsoft Research India. So this is very cool work. I like the idea very much. Just a simple question. So the multipath environment at the device would be very different from the multipath environment at the ear, right? So would that lead to imperfect cancellation, or how do you deal with that?
Right, yeah. So the question is, what your ear device is hearing is actually different from your eardrum is hearing inside your ear, right? So this is a very valid question. So first, the ear device is actually pretty close to the ear. So the difference is...
I'm sorry, I said the IoT device. So you're picking out
sound
samples far away.
Okay, yeah.
The multipath environment there is very different from what it is at your ear, right?
Right,
So,
yeah. So the question is, this IoT device, which is far from me, is hearing something totally different, right? So actually, we do not want the IoT device to hear the same thing as us. So the IoT device provides something called the reference signal, which is one version of the noise source, after distorted with some kind of multipath. We are hearing something different, which is another version, right? But these two versions are very correlated. So actually, the DSP computes something called adaptive filtering. So this filter converts that sound to the sound I'm hearing. And that's actually the challenge of why this noise is not like immediately zero. It gradually converges to zero as you convert this filter.
Thank you.
Hi, Dinesh from Uni Adelaide. Thanks for the talk. The question I have is, in case your IoT relay gets compromised by an attacker and they generate a malicious noise signal, how does your system handle that? Will it still generate an anti-noise signal in the user's earpiece? How will that affect the user experience?
So we have not reached that step yet as to consider the security of this personal device. I would say if this is my very personal device that I carry with me, right, maybe less likely someone is going to attack this device by injecting malicious noise signals. But in the worst case where it is being attacked, this device may be degenerate to the conventional noise cancelling headphones and cancel the sound locally.
Thank you.
Arsenij Zastronych, IPFL. Very interesting talk. It's maybe a half-joking question. What if I just take out the microphone from the Bose headphones and put them on my put the mic on my desk? Would that help already with the performance?
You mean what if I reuse Bose's headphone, take it out, put it somewhere?
Yeah, basically I just break down the existing headphones and put the microphone further away.
Okay. We have not done this experiment because all the components are tightly integrated inside this headphone. But I would say Bose's headphone, I mean the hardware is very high quality in some sense. We are using very cheap hardware. So if we actually put this microphone far away, we are going to enjoy better cancelling performance because the hardware quality is better.
Thank you. That's a nice life hack.
Hi, Naufal Yassin from University of Pennsylvania. Really interesting work. I want to ask, like, if it's possible to exempt some sounds like fire alarm or something like that.
If it's possible to what?
To exempt some sounds from being blocked, like a fire alarm.
You mean you want the option to filter to block some noise and allow some other noises?
Yeah.
Yeah, actually, I would say that's one benefit of our design, which is you have plenty of time to design all kinds of filters and digital algorithms for your application, right? So not only you can now filter some sound, block some other sound, you can also do some other processing with noise cancellation.
Tian, Microsoft Research. Actually, my question was very similar to that, but I encourage you, so one thing that happens in many office scenarios when people want to cancel noise is they still want to be able to have private conversations. So I think one great application could be what you were just saying with enabling an individual who approaches you near your desk to talk to you while you're keeping the device in your ear and allow that conversation to pass through. Like that would directly, immediately help our office scenario like today.
Right.
Do you think that would be feasible with the look ahead and?
So I want the human voice to pass through.
I want to like you were looking in your example, you were trying to cancel Alice, cancel Bob, but maybe you want to allow Bob to talk to you because Bob is very near you, but you want to cancel everything else. And this, this would help many open office setups.
Right. So that's like we add a filter for human voice, right? Yeah, I think this is totally doable. Yeah, thanks.
István Gódor from Ericsson Research. Just curious about how far you are with the research in 3D noise cancellation. Because if you move away the microphone, it at the step it turns to two-dimensional filtering. What about the 3D aspects? Have you already considered it?
Are you saying that sound comes from 3D directions, or?
Yeah. In that case, if you move the mic away from you, then from the sound coming from a different direction, it will have a lag.
Okay, I got your question. So in our implementation, right, we have a dominant sound source which comes from like around similar directions. So actually, you can prove that if you have 3 microphones placed in a nice way, you can cancel the sound from an arbitrary direction in 2D. For 4D, you need 3 microphones, which is for 3D, you need 4 microphones, which is for IoT relays to cancel the sound from some unknown direction. Essentially, because you need the IoT relay to hear the sound earlier than you, right? Yeah, that's the reason why.
Okay, thanks very much. Thank you. Okay, so that concludes the session. Sergey has an announcement.
Yes. As usually, Sergey has an announcement, and actually it's a relevant point because it's a half point of the conference, and it's also a peak point of various diverse activities. So I think you really need an announcement to understand what's going on now. So first of all, topic preview sessions will continue upstairs. We have Steve Uhlik talking about SDN, followed by Alan Zigura talking about wireless. That should be good as well. We of course have lunch in parallel, and then we have a little bit of a kind of deviation for common routine. So after the break here in the ceremonial hall, we're going to have best of CCR session. So those of you who don't know, these are not a paper that went through the SIGCOMM conference review process. They are papers published in CCR over the past year. And CCR editors pick these two papers that they consider the best. So they're going to be presented after that. So it will be 50-minute sessions over here. So in parallel, we'll start the posters, demos, industrial demo sessions. So for 50 minutes, they will be running in parallel with the best of CCR session. And after that, from 3 to 4, we have a dedicated slot. Right? And because of lack of space, the events are distributed between the 3 floors. So essentially, if you haven't discovered yet, so behind the stage, there is northern room. That's where industrial demos are. It's also exhibits by the sponsors. Then going from the southwestern hall in the corner to the northwestern hall in the corner, through the panoramic corridor, there are regular demos that our demo chairs accepted. We had 2 special demos that required more space, and we placed them originally on the 4th floor. One is Explorer paper, which required line of sight. So essentially, your bodily issues will be penetrated by transmission along the hallway foyer on the 4th floor. And also, we originally put the skeletons also in the attic, but we brought them down. So basically, if you're impressed by MIT talk about 3D skeletons, we move them actually not to the northern room, but technically we call it northwestern hall. So it's basically between panoramic corridor and the northern room, basically next to this impressive NetWiser demo. And posters. So posters are very important, and unfortunately, we tried to put everything here on the floor, but we couldn't. Unfortunately, also we have 2 sections of it. So probably you already saw a few poster stands next to the drink bar downstairs in the hallway in the foyer. But we couldn't place anything there. In the last moment, Vigado Fire Brigade told us we have to move posters elsewhere. So actually, most of the posters are in the room called reception area. If you look at the floor plan on the webpage, it's a room immediately when you enter the building to the right. So most of the posters are there. So if your poster presenter, demo presenter be from 2:10 to 4 o'clock, and your stands locations, that's your 2 hours of fame. And also student research competition going on, so those who are competing, be there. Some of the people will be actually your judges, so prepare presentations. So it's pretty much it. So have a nice lunch and enjoy all these events.
I'm not going to manage to cover much of SDN. So if you know plenty of papers or you've got the paper on it and say, oh, you didn't mention it. Yeah, sorry, but yeah, can't fit everything. So really the point is to try to provide a framework and a context for the session that will come tomorrow. I'm not going to say anything about the papers that will actually be there, almost. And also provide some pointers to the literature in case you would be interested in looking at specific aspects I'm going to mention. So that's the plan. First SDN primer. That's actually half of the talk, so hopefully 7.5 minutes. I'm not too sure. So what's SDN, really? Well, when you look at the box or a device, well, the reason why SDN was kind of introduced was from basically the observation that, well, nowadays, routers, switches, and all the network devices, they basically are made of a software that runs the control plane, the routing protocols, the management, everything that is basically managing a forwarding engine. Yeah? And the forwarding engine, that's hardware. Of course, there is a bit of firmware and there is, of course, an interface between the two, but there is kind of a relatively strong separation between those two. So the motivation for SDN is to say, well, we don't live in a world where everything is integrated vertically, but actually things are not monolithic anymore, a bit like computers, where with the appearance of Linux some decades ago now, basically you have a lot of software modularity and a clear separation of like the kernel or the top part and the hardware itself. Same thing for routers. Now, something that's important that is often overlooked is you will not change the existing control plane in the sense that you will not strip or remove things with SDN. What you do is you add a controller that has a global view, that's the good that Jennifer mentioned, that will basically be able, through a communication channel with every single device, be able to instruct the control plane and tweak things in the forwarding engine. Yeah? But that's one additional network hack. So the principle is to have the communication channel between the forwarding engine and the remote controller through some firmware that will run still partly on the control plane of the device. And one of the key aspects, of course, is to allow to expose the capabilities of the hardware so that you can actually do interesting things that before you couldn't do because you didn't have access to that. Or you only had access to the CLI that was provided by your favorite router or switch vendor, and that's all you could do. That was the box view. Now, actually, SDN, it's something that makes sense when you do things network-wide. It's because you want to manage networks. So what you do is you've got your network infrastructure, the same devices as we used to have before. That doesn't fundamentally change. They will basically talk to a controller. So a software entity logically or physically decentralized, or it doesn't matter. It could be one piece of software, but it could be a distributed piece of software as well for reliability purposes. And that controller is that entity that interfaces what we want to do with the network and the network itself. So we've got two APIs. We've got the southbound API, which is the business of handling the network devices themselves. And then we have the northbound API, just for terminology purposes, which is interfacing network applications, and network applications, we'll see later what that can be, that basically whatever you want to do, basically with SDN. So those are called networked applications, but well, it can be traffic engineering, any hacking or thing you want to do to customize the behavior of the hardware. So what are the benefits of SDN? Well, the main benefit is to, in theory, simplify management by providing a uniform API. So anything you do, you will only do it through the API to the controller, and because the controller will be the only way you will interact with devices, not directly, while nowadays you've got central management and then that entity will have to talk with every device. No, you write a network application and you program the network through an API, through the controller. There is a paper this year on Trident that will deal with that is relevant. Another benefit is that you can do virtualization. I mean, we do lots of tunnelings and slicing in our networks nowadays, and it's kind of a mess. So actually, one of the benefits of SDN is to forget about layers, kind of. They still exist, but we forget about them, or when we think about the network, and we basically see things as just one slice virtualization problem, irrespective of the layer at which things happen. So the FlowVisor paper from OSDI 2010 was basically introducing such piece of software that actually lies underneath the controller that manages to some extent the different slices that basically do different things on the network. And the fundamental shift that SDN brings really is that in terms of what you do on the network, so instead of using network hacks and abusing like routing protocols, so tweaking IGP weights, changing BGP, messing up with peering sessions, doing all sorts of nasty stuff that have nothing to do with the purpose of what those protocols were intended to do. So you typically don't know whether they are really side effects, or you hope it's not the case, but you're not too sure. Now you logically think in terms of applications on top of the controller, and you say, I'd like to do this. This is what I'd like to implement or have on the network. And then basically the controller will have to have an API or a module that basically knows how to translate that into how do you handle the network, but in a way that will be hopefully consistent in terms of the management of the different devices. So for example, to do traffic engineering, we'll mention an example, but I already mentioned it, like the Google B4 work, network monitoring, or security, or whatever you want to do with the network. So for thinking about the network and what to do in terms of changing the network, it's just a cleaner way. It's not better, it's cleaner, conceptually speaking, yeah? So I'll go fast on that because I hate protocols. Yes, I teach networking, but I hate protocols. What happened? Can I have my slide, please? Thank you. Not too sure what happened. Doesn't matter. So, boring protocols, well, yes, of course. There is one main realization of SDN, that's OpenFlow. It's a set of protocols and API. So, as usual, there is a protocol to do the sessions, the messages, blah, 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 statistics as well. And then the configuration part, which is, well, how do you reconfigure really the devices, so the network management per se for operators. That's a view of what OpenFlow 1.0 looks like from a data plane perspective. So SDN, yes, it controls data plane separation, but it's also handling flows and what happens when packets arrive at a device differently. So the principle is to have match actions and potentially monitoring. So what you do is you receive a packet at some device that supports SDN, you match based on the header and say that's a flow, basically, whatever flow means depending on how much you have freedom, and you have lots of freedom in terms of the header space. You get the table, a flow table, which is basically more like the forwarding information base that we have today. But today, it's destination prefixes. That's the only thing we can do. While here, you can have any type of flow that is based on the header. And then, once you match that, you have a new entry. Well, the controller will have to put that entry. And once you have an entry, you classify that flow as a specific entry in the table, in the fib, and then you want to do something with it. You say, well, that packet, don't like it, I drop it. Or that packet, I want to multicast or broadcast it. Or I want to do, well, whatever you can do or want to do when you receive a packet and you want to do something with it and throw it somewhere else on the physical device. So that's basically the action part. And then I like measurements, so I like the statistics part. You can also have counters, and this is 1.0, but there are definitely more versions of OpenFlow, like should be 6 now. And there you can do more complicated statistics with multiple layers of tables. So you can make more complicated statistics if you want. So when you look at the controller, well, it reflects basically what SDN is about. You've got applications at the top that do something like, well, load balancing, data centers management, traffic engineering, whatever you want. Then you've got that API that's really not standard at the moment that will be used to communicate with really the controller part that is not what the user does, but that is basically the equivalent of a kernel type of thing. And then you have basic services because you have to do topology discovery. You need to know your network. You may need to do path computation if you say, well, I don't trust my routing protocols, or I want to have specific paths that are not those that are computed by the routing protocols. And then you add other modules. And then you've got, of course, the protocol engine so that you basically can reconfigure and do the protocol dynamics. Now, I will mention only a few open issues and applications. I won't cover everything, but just enough so that we cover all the papers of the session. How am I doing? Oh, I have to go fast. So open issues, one is monitoring. I like that. I put it first because I like measurements, but it's not like it's more important. And one issue, of course, is when you have flow-level measurements, you can have a lot of flows and a lot of data from your devices, so that probably won't scale unless you do things on a very small subset of the traffic. So one of the papers we'll have tomorrow, Sonata, kind of handles that. It's also called telemetry. That's an older word for that. And there are a few other papers on measurements. The main issue is, yes, you decouple control data plane and you say, oh, yes, I will cleanly add another hack and change things inside the network. Well, yes, but when you do this, you better know what you're doing and whether it interferes with other slices protocols. So you want to be sure there is congruence, so consistency between the control and the data plane, so that what you think the controller knows is the reality. While today, for example, we don't really know. We have routing protocols, and they react so fast that actually we never know the actual state of the network, because by the time we have that information, well, the routing protocols will probably have converged or changed something. So we don't really know the state of the network, while here, hopefully, it's still going to be delayed to some extent, but you have a better view of the network, or you can. Now, there are, of course, issues with performance overhead. So the DevOflow paper at SIGCOMM a few years back was handling that, because, of course, if you have lots of flows, you need to be able to manage them at scale. So if you have thousands or millions of them, well, you need to be able to handle it. And then, of course, because the control and data plane are decoupled, well, then you need to make sure things are not wrong. So you need to test, like, for example, the OFLOPS paper that was looking at, is my switch really doing what I think it should be doing? And quite often, when you send packets and you look what's really going on, and when it's happening, it's not quite what we thought, or because hardware behaves slightly differently from our expectations, because hardware may do other things. And actually, that's the only time I'm going to mention workloads, which is tomorrow's paper that will actually handle workloads for NFV, which is like SDN, but slightly different. So one open issue that's related is the network updates. So when you change the network, again, you want to make sure that they are that things are done properly, and that's more distributed systems type of problem rather than networking, but you want to have correctness, so to be sure that things are provably correct before you start messing up with the network, that things are consistent, so that there are no incoherence like loops or things that basically stem from interactions within your system, that basically updates are ordered in the right way, because you transition from one state to another, that might need intermediate steps to go from a network state to another, and be sure that the data plane basically does what you really want. Security, that's one of the open points. Like, I had to mention it because I think it should be mentioned, but actually there is not much. And I didn't find many papers besides really a few surveys that are relatively high level, so I mentioned them. But the problem with, of course, yet another hack and doing things with a communication channel is that you have potentially issues with the controller, software bugs, or access to the API. Same for the communication channel, whether that's southbound or northbound. You've got virtualization, so you may have ways to abuse slices and interact between them if you want, and same for the data plane. So the most related thing really is going to be the network verification session that will happen later. But it's, again, verifying rather than fixing security issues at the moment. So I already mentioned a few applications. One is traffic engineering, just that I worked on it, so like I mentioned that. So the B4 paper, and then there is a B4 plus that was yesterday. And then you've got monitoring, for example, that requires advanced data structures if you want to scale things in terms of number of flows at the speed we want for the data plane. Two examples of papers. One will be tomorrow on the Elastic Sketch. And that concludes my talk, and the rest are all further reading that are just for your enjoyment. Thank you very much.
Thanks a lot, Steve. In order to thank you, we have a small token of our appreciation. Wow. Something to remember the Hungarian cuisine.
With a dedication from you. Thank you. Nice.
So any questions you might have for Steve, he will be around. Our next presenter is Ellen Segura, professor from Georgia Tech, and also a member of the SIGCOMM Technical Steering Committee, and she will be telling us all about wireless low data rate and low power and high data rates.
Thank you. I will not be telling you all about this, but I will tell you something about them. Okay, so thank you for being here. Let's go on a journey. The journey heads down the stack from the application layer all the way down to the physical layer. So the papers in this session are almost entirely physical layer papers. There's a little bit of MAC protocol in one of them, but the rest are really very heavily focused on the physical layer. And I may have been a sucker in agreeing to do this preview talk because my own work and experience is not in the physical layer. I do have an electrical engineering undergrad degree, which I tried to dust off. It had a lot of dust on it. It's from 1987. All right, you're here and it's okay. How I learned to stop worrying about congestion control and love the physical layer, at least temporarily. So this talk is not for phi layer researchers, unless they, I guess, want to be amused by hearing someone describe the phi layer who doesn't actively work in it, nor recent electrical engineering graduates, not also for people who doodle with these kinds of symbols, and I'm not referring to the scheduling process of doodling, but rather the drawing by hand. And if I say something incorrect, please feel free to tell me offline. I actually would like to know. Don't tell me now, though. Okay, so how many of you are actually very familiar with these symbols that are on the right-hand side? Which is your favorite? Do you have a favorite? Which is your favorite? The conductor. And how about you, Steve? Which is your favorite? My favorite is the diode. Okay, so the diode allows current to go in only one direction and not the other, and actually it has a role to play here. Okay, there's a lot of good cartoons about the physical layer. If you need to contact me, you can reach me on my cell. all right, this is the basic principle of signaling. So wireless physical layer 101, all right? There's a transmitter, there's a receiver, they have antennas, there's a channel. On the channel, you put a signal with a frequency and amplitude, and if everything in an ideal world, which we never have, what goes in is what comes out. So much of the work in wireless physical layer is to essentially try to make things as fast as possible while respecting power constraints where they are present, and also dealing with the imperfections that arise on the channel because channels don't behave well. Anybody know what this is a cartoon from? It's a little old now. You have to be of a certain age. What's that? You are apparently of a certain age, as I am too. What is it? What is it? Argyle Sweater. This is the Far Side. Far Side. Far Side was a fantastic cartoon series of a certain time. Potato salad has eggs in it usually, and if things that have eggs in them can go bad, so this potato salad is holding up the condiments in the fridge. Okay, so bad things can happen on channels, including attenuation, which is greater with distances, and distortions. If you attended yesterday, the session that included communicating through the air-water boundary, or communicating through the air-human body boundary, what you saw there is that those transitions are especially bad for channel characteristics. You both face reflection when you cross those boundaries, and you face significant attenuation, that is a decrease in the signal as you cross those boundaries. So antennas are really, with the exception of one of the papers in this session, antennas are fundamental to the work that these authors have done. And in case you don't know, an antenna converts electric current to radio waves. And vice versa. And antennas have this nice property called reciprocity, which is a really nice property in the world. We don't see it often enough. It means they act the same as receivers and as transmitters. So very nice property. Antennas can be monodirectional, meaning they radiate power everywhere, or they can be directional, which means that their power is concentrated in a particular direction. And especially when you want to increase speed or reduce power, you want directional antennas so that the majority of the signal power goes where you want it to go. I mean, assuming you have a single destination in mind, goes where you want it to go. This figure, I'm not going to explain. It's kind of it turns out there's a whole vocabulary for indicating properties of antennas. Does anybody in the room know what this actually means? Sort of. I mean, it's going like this 4 times per minute, all right, and other stuff is happening. To make up for it, I put this joke that I found on the internet, which is so silly as to be extremely funny. You're not laughing, so I'll just assume that you're laughing inside. Okay, so now beamforming. So antennas are central to the papers in this session. Beamforming is also central to the papers, most of the papers in this session. And the idea of beamforming is if you use multiple antennas, you can direct them, play around with them, so that their energy gets essentially adds together rather than interfering with each other. And if you get that right, then you get this fantastic event at a receiver, which is you get sort of the combined energy of multiple antennas, but no one antenna has to put out all that much power. So beamforming is the process of essentially getting the antennas phased correctly so that this coincident constructive interference happens. And you can do this, you can face this problem of wanting to do beamforming in settings where the antennas are co-located and tightly controlled, and phased arrays are an example of that, and I'll show you that in a minute. Or they can actually be not closely located, and you can still want to coordinate their directionality and their phases so that you get this constructive interference. And Massive MIMO is an example of this non-co-location. One of the papers in the session is about massive MIMO, and more specifically about distributed, truly distributed massive MIMO. Okay, so a phased array is kind of a cool component. So the way it works is you have a set of antennas, and you have a radio frequency source that's power is then divided up across the antennas, and there's control that controls the phase shift of the antennas. And when you apply a particular phase shift, you get, this probably has a, I hate these, all right, I won't use it. When you apply them, you get constructive interference primarily in a particular direction. So if you change the control, and that direction's theta up at the top. If you change the phase, you get a different theta angle for the place where the maximum constructive interference is happening. So if you have this thing, you can play around with the control, and you can basically send the most constructive interference to a particular place. And furthermore, certain places you'll be able to get more constructive interference. So it's not that you get the exact same kind of amount of constructive interference, no matter what direction you go. It changes depending on how you've set the phase. So this is a phased array. So the second paper, the order of the papers that I'm going to go in is not the same as the order in the program. Second paper has to do with doing this wave beam alignment when you are in the millimeter wave portion of the frequency spectrum. So the reason why you would want to be in the millimeter wave portion of the frequency spectrum is that gives an option for bandwidth usage that previously wireless has largely not tapped into. So it's a new portion of the space. If you understand what's going on, if you nod when I say the right thing, it'll make me feel really great. Am I right? Yeah? Okay, so it gives a portion, more or less. He's like, not exactly, but, okay. So it gives a new frequencies to make use of. Okay, but a property of that portion of the frequency spectrum is that you get rapid attenuation with distance. So phased arrays are useful, maybe even almost necessary to operate in the millimeter wave portion of the frequency spectrum. And then you're going to get this very narrow beam, and you have to get these two, the receiver and the transmitters, aligned so that when the beam is narrow, it actually is received at the receiver. And you want to do it quickly. Okay, so this combination, really this issue of quickly poses quite a substantial challenge, because you'd like to avoid kind of a brute force walking through of all possibilities and then seeing which one produces the maximum power. You'd like to do something more efficient. And this is a beautiful diagram from the paper that I won't describe, but the hint is that you should, this is really the key idea, okay? So when you're listening to the talk, this is the part you really want to get. Okay, and it's the method by which this alignment happens quickly. Okay, so the first paper also uses multiple antennas and beam forming, however, in a very, very different context. It's actually a much lower frequency portion of the frequency spectrum, and that's because this is a paper about communicating with and powering a battery-free sensor that's in the human body. So here the idea is there's a sensor inside the body. You don't know precisely where it is, so that's a challenge. You also can't communicate with it because actually you're trying to power it. And so you have a rather challenging problem with respect to, eventually you'll see beam forming, multiple beams, and trying to locate and power this device. So there's this incredible, unbelievably simple circuit that does energy harvesting. It has two diodes, and for those who like capacitors, yay, it has two capacitors. It has no resistors. Sorry. Resistors are useless, apparently, for energy harvesting. So if you put a signal into this, including if this circuit is inside the body and it receives a signal, it will store energy. So that's so cool. And it's so simple. That's crazy. So in two different phases, it does two different things depending on which part of the phase you're in. And the bottom diagram, the top diagram comes from the paper. The second one does not. But the second one, I think, more clearly shows that you get, partly because these diodes that are the coolest of the devices have this property that they only let current go in one direction. In the different phases, you either go through diode 2 or you go back through diode 1. Okay, so it's not, the paper doesn't invent energy harvesting, but the paper makes substantial usage of it for this this task. Okay, so you're trying to get power to this sensor that's in the body whose location you don't know and that you cannot get feedback from. And so again, the idea here is to take multiple it's in the body, so you have everything is bad. The bad things are happening to the signal. You can't use high power. You really have an extremely challenging situation. When you cross the air-body boundary, bad things happen. So again, it's a form of beam forming with multiple transmitters and different frequencies, and then combining in what the authors call coherent beam forming or coherent incoherent beam forming, one of those two. So anyway, you'll find out which one when you go to the talk. Okay, so now moving away a bit from the antenna array and the smallish number of antennas related to this powering sensors in the body, let's talk about other ways to have more antennas. Okay, so MIMO, multiple input, multiple output, it just means you have multiple antennas at the transmitter, multiple antennas at the receiver. And in traditional MIMO, you would have a fairly small number of these antennas. Massive MIMO, as you can tell by the name, is essentially the use of many more antennas, hundreds of antennas at a transmitter and potentially at a receiver, but it's useful also if it's just at the transmitter. Now, in distributed MIMO, the antennas are not co-located. Okay, you have lots of them. I didn't draw 100. You have lots of them, but they're not at the same location. And so, synchronizing them, getting them to beam form and work properly, is a more challenging problem because they're distributed. Okay, and the general idea so you're trying to synchronize their oscillators to a common reference phase. And one way to do that when you have distributed antennas is that you have a leader, and the leader is in charge of sending out a reference signal that everyone can hear, and that's what all the other antennas synchronize onto. Okay, and so that works fine, except everyone has to be able to hear the leader, so there's some scaling challenges. If the leader is taken out, then the usual problems. That's not good for resilience. And when you add nodes, you have to be very careful that they're within range of the leader. So this paper, which is the last one in the session, is called Chorus, Truly Distributed MIMO. And the general idea here is to remove the leader, so all nodes are acting as peers. And the trick there is that they will essentially listen to each other and form a sort of synchronization reference signal with their neighbors, and then that sort of propagates throughout the space. And this is another beautiful diagram from the talk, and they'll explain to you what this means. It has to do with the reuse of frequencies. Okay. The last paper, which I'll say the least about, and I'm out of time anyway, is now moving away from the antenna world, sort of, certainly away from the multiple antenna world, into the radio world. And the idea here is, if you want a radio that can operate at low power, yet still is on all or most of the time, for example, because you're streaming sensor measurements, so you can't afford, so duty cycling, turning off the radio and turning it back on again is an obvious way to save power. But if you need to be transmitting most of the time, even at low rate, duty cycling is problematic. So the idea of this polymorphic radio paper is to mix active components, and those are examples on the left-hand side, including diodes, with active components which must be powered with passive components that don't require power, to produce a radio that can operate in either passive component mode or active component mode, and you switch between them as appropriate for the communication. So, and the good thing about that, of course, is, so in some sense, it's a little bit like duty cycling, except in the off, you're not totally off. You're in the passive portion, and then in the active, you're doing it adaptively, not according to some regular period between on and on. So you then switch between these, and it's challenging to do that without application impact. And just, this is a picture from the figure. This is the the end device, the cell device or IoT sensor that's using this polymorphic radio. And I just want to point out for you that there are two halves to this picture. The top half is the transmitter circuitry. The bottom half is the receiver circuitry. And in each case, there are then two pathways, a passive pathway, which contains passive components, and an active pathway, which contains active components. And then there's and then the antenna you see on the left-hand side. So when you see this talk, this gives you a reference point. You need both types of capabilities in both directions. All right, so that's the end. Thank you. The authors, these papers, I decided I would read only N pages, where N initially was 4. I thought that was perfect. Then I had to extend N to 8. So these were very nicely written papers. Justine Sherry told me not to prefetch the talks, so I tried not to prefetch the talks. And thank you for listening, and I don't know, taking away something. So thank you.
Thank you very much. Also for you, of course, for very nice. Thank you, sir. And that was it for this topic preview session. The next one and the last one will be tomorrow, again around lunchtime, and then we will have David Walker talking about network verification and Walter Willinger talking about measurements. Hope to see you there.